Okay, so let's go ahead and get started. If you hadn't picked up your test, they'll be up here at the front to pick up at the end. But we want to get going. So I gave you guys this problem at the end of class last time as something to work on for homework. And so I want to give you a couple more minutes to work on this, and then we're going to talk about this question. Okay, so go ahead and talk about this, and we'll talk about it in a couple minutes. All right, so let's go ahead and solve this one. So something interesting you guys might be finding as you're going through this is there's kind of a couple of different ways to approach this problem depending on how we're defining our origin. So in the question, it provides you with an origin to start with, and what that says is that I'm going to say that the height y is equal to 0 is where these two start. So what I'm going to do is I'm going to solve it both using that definition and then using another definition that I saw a lot of you guys were using, which will also give you the correct answer. So when we look at this, we have our initial state and we have our final state. Since we want to apply conservation of energy, this means that what we're going to say is the initial energy is going to be equal to the final energy. And each one of these has some kinetic energy and some potential energy in principle. So we can say that EI is equal to KI plus UI, EF is equal to KF plus UF. Okay. Now that we have this kind of written out in general terms, let's look at the physical situation that we have and see if perhaps some of these terms might be 0. And so when we look at this, we know that we're releasing this from rest. That means that the initial velocity of the system is 0, which means that the initial kinetic energy is 0. Now, for this choice of coordinate system, we also know that because the potential energy U is going to be equal to mgh, the initial potential energy is going to be 0, because for this choice of coordinate system, we're saying that 0 is where the two masses start. So that actually says that the initial energy is going to be equal to 0. Now let's see what we can do to write the final energy. So for the final kinetic energy, because these are constrained to move with the string, and the string doesn't change length, these two objects are going to have the same velocity at the end. And so this one's going to be going up with some v, this one's going to be going down with some v. And so this kinetic energy is going to be written as a sum of two kinetic energies. So this is 1/2 m1 vf, or we can just write it as v squared, plus 1/2 m2 v squared. Okay. Now, the next thing that we need to write here is the potential energy. So in order to write the potential energy, what we do is we say that this object is a height h above the origin. This one is a height h below the origin. And so when we write our potential energy, we have to say that for the mass m1, this is going to be m1g times h. For the mass m2, this is going to be m2g times minus h, right? Because this is below the origin that we have here. So we can put all this together and solve for the kinetic energy. And so let me write out some of the algebra and steps here. So we have still have some stuff written over here. We have 1/2 m1 plus m2 times v squared plus m1 g h minus m2 g h. So this is going to be equal to 0, and what we'd like to do is we'd like to solve for what the velocity is. So in order to do that, I can move this term to the other side. So this is going to give me this is going to give me an m2 minus m1 times gh is going to be equal to 1/2 m1 plus m2 times v squared. We can divide both sides by m1 plus m2 and also multiply both sides by 2. So this gives me a v squared is going to be equal to m2 minus m1 gh divided by m1 plus m2, and then we can solve for the velocity by taking a square root. Okay. Now, when we evaluate this and plug in the numbers, what we end up seeing is this gives us an answer of 1.1 meters per second, which is answer choice B. Okay. So this was one way to set up this equation, but what I want to do is I want to show you that we could have chosen the other origin. We could have said that the ground was 0, and we'd end up finding the same answer. And so when we do that, our initial state, we still don't have any kinetic energy. Kinetic energy is 0 because these aren't moving. But now, if we choose the origin to be down here, we're going to have gravitational potential energy from each one of these objects. And so our initial energy is going to be equal to m1 gh plus m2 gh, right? Because each one of these objects is this height h above here, okay? Now, when it comes to writing our final energy, we're still going to have the same kinetic energy. So EF is going to be equal to 1/2 m1 plus m2 times v squared. Now, here's the thing that's going to be different. When we write our final potential energy, this m2 is going to have 0 potential energy because now it's at the height 0 here. And m1 is going to have a potential energy of m1 times g times 2h. So this is going to be plus m1 g 2h. Okay. Now, if we set these two equal to each other, we end up finding this is m1 gh plus m2 gh is equal to 1/2 m1 plus m2 v squared plus 2 m1, sorry, this should be, 2 m1 gh. And to make this look the same way that it did for this initial equation that I had here, I can move both of these terms to the other side. And when I do that, you see that we end up recovering exactly the same equation, just as we should. So what this tells us is, we can choose to put the coordinate system wherever we want, but we just need to be consistent with that choice, and we need to be careful with the way that we're defining the potential energy as a consequence of that choice. Okay. Any questions about this? Okay. So let's move on to another one. Okay, so now what we want to do is suppose that the masses have an initial speed of 0.2 meters per second and that mass m2 is moving up. How high does m2 rise before coming to rest? So we're still playing around with the same picture that we have here in some sense, but we're changing the conditions. And what we're going to see is it's just going to change the terms that we have in our conservation of energy equation. Okay, so take a couple of minutes and talk about this one. Okay, so let's go through this one real quick. So for this one, the setup is very similar to the last one, only the parameters are slightly different because the situation is a little bit different. So in the last one, we said we have these two and we release them from rest. M2 is naturally going to go down because it's got a larger mass than M1. But in this case, what we're doing is we're saying, well, somehow we kick M2, so it's moving up. So M2 is moving up with some velocity. M1 is going to be moving down with some velocity. So what we want to do is we want to set up the equations for our conservation of energy here. And so in order to do that, what I'm going to do is I'm going to use the case where we're saying that the origin here is going to be 0, okay? So I'm defining the origin to be the height that these are both at initially. And so what that allows me to do is to write the initial energy. In general, this is Ki plus Ui, but because I'm saying the height here is 0, the initial potential energy is 0, okay? Now, let's look at what's going to happen with our kinetic energy. So if these are both moving with some velocity v, then what that says is that the kinetic energy is going to be 1/2 m1 plus m2 times v squared. So here's our initial energy, okay? Now, we know that in this case energy is going to be conserved, and so what we can do is we can write the energy in the final state, and then we can equate that energy in the final state to the energy in the initial state. And so when we do that, what we can say is that EF is going to be equal to KF plus UF. But when we look at this, the kinetic energy in the final state is going to be 0, because what we're trying to find is how far this is going to go. So the furthest that it goes is when the velocity is going to go to 0. That's the point where it's going to turn around. And so because of that, the kinetic energy is 0. Now what we want to do is we want to look at the potential energy. So to find the potential energy, we say that UF in general is going to be mgh, but now we have to look at what our coordinate system tells us here about whether these are going to be positive or negative. So if we look at the mass m2, this is some height h above this origin that we have here. And so this one's going to give me a plus m2 gh. If we look at the m1, this is going to be below, and so this is going to be minus m1 gh, okay? And so now that we have this final potential energy, we can equate this to the initial energy that we have here. So we have 1/2 m1 plus m2 v squared is going to be equal to m2g minus m1g times h, okay? Now, we want to solve for what this h is, and so in order to do that, we just divide both sides by m2g minus m1g, and so this is going to be 1/2 times m1 plus m2 divided by m2g minus m1g times v squared is equal to h, okay? And so when we plug that into our calculators, what I end up finding is an answer of 4 centimeters, okay? Any questions about this one? So, like I said, the setup's a little bit different because the situation is different, but the mentality that you should have and the way that you're thinking about these questions, it should be the same. You should be asking yourself, what is the energy in the initial state? What is the energy in the final state? And then if you can write those two things, if energy is conserved, then you can equate them and you can solve for whatever it is that you need to solve for. Okay? Any other questions? Yeah?
What was the answer again?
4 centimeters. Yeah. Okay. So, moving right along. So, now what we want to do is we want to talk about a quantity called power. And the way that power is defined, power is the amount of work done per some time. So you can define power in a couple of different ways. You can define it as the P, which is going to be the work per time, or you can say that this is also equal to the product of the force and the velocity. Okay. So go ahead and use that definition and calculate this one right here. And what you'll find is the answer you get won't be exactly one of these, but it'll be closer to one of them than any of the other ones. Okay. Okay, so let's go ahead and talk about this one. So for this one, we're told that we have this 84 kilogram Marine that's climbing this rope that is 12 meters high. And so he does this in 8 seconds, and we want to find what the power is that's consumed in order to do this. And so I gave you this equation. The power is going to be equal to the work divided by the time. And so we know what the time is. This is going to be the 8 seconds, but we need to know what the work is. So in order to find what the work is, what we can do is we can say that the work in general is going to be the force times the distance times the cosine of the angle between them. But in this case, can we settle down, guys? It's distracting. So the angle between the force and the distance is going to be 0, right? So these are in the same direction. So the force that we have here is going to be the force due to gravity. This is mg, just mg, times the distance that we have here. We can just say this is the height, okay? So we can take this and we can plug it into this equation. So what we have is P is going to be equal to mgh divided by T. And then when we plug in the numbers here, we end up finding something that's close to 1200 watts. Okay? Yes?
We didn't using force times velocity. That was
well,
the same answer.
The thing that you have to be careful of there, I mean, I guess what you could do is you could, it ends up working the same way, because what you have then is the force is going to be mg.
Yeah.
The average velocity is going to be the height divided by the time. So this would be h divided by t. So it ends up, you kind of have exactly the same equation.
Yeah.
Yeah.
Okay.
Okay. Other questions? Okay, so we gotta skip through a couple of these because I want to make sure that we're getting to momentum today. So I have one more difficult question for conservation of energy, and the thing about this one and what makes this difficult is the fact that we are incorporating friction now. So we're going to have a situation here where energy is not exactly conserved, right? Because in order for energy to be conserved, you need to say that there are no non-conservative forces acting on the system. So this was the case that we were talking about last week when we said that if I had some point here, call this point 1, and we had some point 2 up here, and we could even say point 1 is the bottom of an inclined plane, point 2 is at the top of the inclined plane, that the energy, I can write the energy here, and I can write the energy here, and if there's some non-conservative force acting between these 2 points, what we say is that the change in energy is going to be equal to the work done by the non-conservative force that acts between those 2 points. Okay, so here what this says is we can calculate what the energy is here, E1, E2, then E2 minus E1 is going to be equal to whatever the work is done by the non-conservative force between those 2 points. Okay. So go ahead and talk about this one. This one's purely algebraic, so there's no numbers required here. Don't worry about doing number 1, just do number 2, because we're a little short on time. It's a good exercise to show that both of these methods will give you the same answer, but we don't really have enough time to show that. But if you want to do this in your free time, it's a good exercise, like I said. Okay, so go ahead and talk about that, and we'll talk about the answer afterwards. Okay, so let's go ahead and talk about this one. So what we have here is we have this block moving with some initial velocity v0. It has some mass of m, and it's going up this inclined plane that makes an angle of theta relative to the horizontal. And what we'd like to do is we'd like to find an expression for the distance the block makes it up the inclined plane. Okay, so in order to do this, I actually wrote this down here already. We're going to use this this equation that comes from the Work-Energy Theorem that says that the change in the energy is going to be equal to the work done by the non-conservative force. So what this allows us to do is define what the energy is here and here. We take the difference between those, and that's going to be equal to the work done by the non-conservative force to move that acts as we move between those 2 points. So the first thing that we can do, let's define E2. So when it gets to the top here, we say it's going to not be moving anymore. And so what that says is that there's no kinetic energy. This is only gravitational potential energy. And so this is going to be m times g times h. If I define this height here, I'm also going to define this distance. And we'll come back to relating those 2 things together at the end. Okay. Now E1 is straightforward as well, because when we look at E1, if I'm defining my origin here, which is what I kind of indirectly did when I said this E2 was mgh, then the gravitational potential energy at the bottom is 0. And there's only kinetic energy at the bottom. So this is going to be E1 is equal to 1/2 mv0 squared. Okay? So we've already gotten this left-hand side. This is just going to be mgh minus 1/2 mv naught squared. Now, in order to finish this calculation, we're going to need to figure out what the work is done by friction here. And in order to do that, what we can do is we can draw a free body diagram here. So let me rotate this a little bit more. So we have normal force, we have the force of friction, we have gravity, okay? Now, in general, if an object is moving, the force of friction, F, is going to be equal to mu times N. Okay, so now that we know this is the force of friction, we need to determine what the normal force is. And in order to do that, we could sum our forces in what we can call the y direction. So this is the plus y direction. And what we see ultimately is that this normal force is going to be equal to mg times cosine of theta. Okay, so we can take this and we can plug it in here, and so we see that this is going to be mu mg cosine of theta. And then we're almost there to finding the work done by the non-conservative force. We just need to remember that work is going to be equal to force times distance, right? So in order to find this work done here, we multiply this by the distance that we have, and we take into consideration the fact that the force is going to be pointing down the plane. We're moving up the plane, and so this work is going to be negative. And so when we do that, we end up seeing that this is going to be equal to minus mu mg d times cosine of theta. And so we're almost there. We just need to relate h and d. And because we have this triangle here, we have this angle theta, the hypotenuse is d, we know that sine of theta is going to be equal to h divided by d. And with this now, we have the solution fully parameterized. Okay? So just to kind of talk through this again, we can say that the change in energy, or the difference in energy between the final state and the initial state, is going to be equal to the work done by the non-conservative force. We can say pretty readily and pretty easily at this point what the energy is here. We can say what the energy is here. Then we can figure out what the work is to go from here to here, and then the difference between the energy in the final state and the initial state is equal to the work done by the non-conservative force between those two states. Okay? Any questions about this? All right. So, and I'll post this online, so you'll be able to review it again. So, in the last 15 minutes, what I want to do is I want to start talking about a concept called momentum. And so we posted the video online, but I didn't update the link on the week at a glance, or the pacing guide. So I'm going to kind of go through some of the things that I talked about in the video, but try to watch that video before the next class. And so the important thing to take away from momentum is how it's connected to the force initially, and then we can start talking about applications of momentum. So when we think about an object that gets moved, or that has some velocity associated with it, a lot of times what we like to do is to think about what caused it to have that velocity in the first place. And that's what kind of draws us back to discussion of Newton's laws. And so what we can define in terms of momentum that relates to the force is what's called impulse. The impulse is defined to be the force acting on an object times the distance, or sorry, times the time over which that force acts. So if I have my this was a rock that was left here that looks kind of like a petrified avocado, if you want to see this later. But there are geology classes in here, so I guess that's why this is here. But if I want to move this and get it to acquire some velocity, what I can do is I can apply force to it, okay? So I apply the force over some time, and that's going to change its momentum. So the impulse is defined to be the change in momentum for an object, where the momentum, P, is going to be equal to the mass of an object times the velocity of an object. Now, in some intuitive way or some colloquial way, this definition of momentum makes a lot of sense to us. Because if you think about objects of different size or objects with different velocities, you can have some intuition about what has a large momentum or a small momentum. So if you think about a bullet has a pretty small mass, but it moves really quickly. So you'd say that's something that has a very large momentum. You could say something analogous to a train car if it's not moving very quickly. That's something that has a lot of momentum even if it's not moving quickly because it has a very large mass. And so what we can see then from this equation is that the product of the mass and the velocity is really what dictates what the momentum is of an object. Okay. So that's just a short spiel on this, but make sure that you watch the video because it's going to go in a little bit more detail than I did just now. So when we talk about momentum, something that we're interested in is collision. So we have two objects that can move towards each other and strike each other. And the statement of conservation of momentum is the statement that the sum of the momentum in some initial state is going to be equal to the sum of the momentum in some final state. And this kind of harkens back to conservation of energy, right? Because we said something about some initial state. We say something about some final state. And whatever is going on in the initial state is going to be equal to whatever's going on in the final state. And so in posing this, something that we like to talk about are collisions. And so there are several types of collisions. So an elastic collision, an example of an elastic collision is when two things hit and they bounce, okay? And a perfectly elastic collision is when they bounce perfectly. So in the case of an elastic collision, kinetic energy is conserved as well as momentum. We also have inelastic collision. So an inelastic collision, or a perfectly inelastic collision, is when an object comes in, it sticks to another object, and they move off together. So in those cases, only momentum is conserved. So something you could say in an inelastic collision, you could have the reverse happening as well. So you had two objects and they kind of blow apart. That's another example of an inelastic collision. And so, yeah, then a perfectly inelastic collision is when they stick, and an inelastic collision in the language of this slide is when they kind of stick. We're typically only concerned with perfectly elastic and perfectly inelastic cases. Okay. So we want to look at this conceptual question in terms of the definition that I have here for momentum and ask ourselves, we have two cars. Car 1 has a mass of m and a speed of v going east, and car 2 has a mass of 2m and a speed of 1/2 and it's going north. And you want to know, do these two have the same momentum? Or your friend Tobias says that they do, and do you agree with him or not? So go ahead and talk about that. So let's go ahead and talk about this one. It's a little bit of a trick question, but not really. It comes to the fact that this is a vector equation. So we had a nice break from vectors when we were doing conservation of energy, but vectors are back, and we need to take in consideration when we're dealing with vectors the direction that things point. And so when we're looking at these two cars, with car 1 moving east and car 2 moving north, these two objects are going to have the same magnitude of momentum. That's true, but their total momentum is not the same because they're moving in different directions. Okay? Okay. All right, So now let's look at this one. So object 1 has a mass of m and speed of v. Object 2 has a mass of 2m and a speed of 1/2 v. Which of the following statements is correct? Now, something to take into consideration here, the momentum as written here, these are magnitudes of momentum, right? Because they don't have vector signs, these are treated as magnitudes. Okay? So go ahead and talk about this one. Okay, so let's go ahead and talk about this one. So when we look at these two objects, let's write down what the masses are and what their velocities are. So for object 1, this has some mass m and some velocity v. So we could calculate this momentum. So P1 is just going to be equal to mv. Okay? We could also calculate the kinetic energy. So K1 is going to be equal to 1/2 mv squared. All right? Now, for object 2, we know that this one has some mass of 2m and it has some velocity of v over 2. So to calculate P2 is going to be equal to 2m times v over 2. So this is going to be mv. So this one tells us that P1 is equal to P2. And then to find what the kinetic energy is, what we can say is this is K2 is going to be 1/2 m, which in this case is 2m, times v squared, which is v over 2 squared. So this is going to be 1/2 times 2m v squared over 4. This cancels this, so I get a factor of 2 here. So I have an extra factor of 2 here, so this is going to be K2 is equal to 1/2 times 1/2 mv squared. And so this says that K2 is equal to 1/2 times K1. Or K1 is equal to 2 times K2. Okay? And this is going to be answer choice F. Okay? Okay. Now, I actually don't have this demo, but that's okay. So, actually, we'll go ahead and stop here for today. So I'll give you guys a little bit of a break. So we're going to come back and keep going with this on Thursday.